All right, all right. So now that we got a couple of basic definitions under our belt, let's continue with talking about surveys and what we can do with those things. So this section, oops, didn't mean to start right there. Let's go back to the beginning. You see lots of information. It's talking about measuring the quality of our survey, okay? So we as statisticians, okay, we evaluate our method, not the outcome, because our method is super important for us. Because if we don't take a look at how we arrived at this, we might have outcomes that we can't really trust. Okay, so the outcomes are great, but if your method is poor, then your outcomes are junk. Okay, so we as statisticians, we evaluate the method, not the outcome. So what we mean by this, just a couple of things, is we look at bias. Okay, and we've talked about bias before, but now we're going to kind of put a little bit of math behind it. Okay, so bias mathematically means that it's the distance between the center of the sampling distribution and the population parameter. Okay, so in general, what we're looking at is p hat minus p. Okay, we're looking at p hat minus p. We want to know how far away are we from our population parameter. In most cases, we're going to be dealing with the proportion. Okay, how far is our proportion from the sample from the population proportion? And then the other piece that we use is what we call precision. Okay, precision is the standard deviation of the sampling distribution. Okay, it is the standard deviation of the sampling distribution. So hence you can see that standard deviation formula right here for us. We also call this SE, which stands for standard error. Okay, standard error. So we like to use standard error with the population parameter, but if we do not know the population parameter, then we can use p hat in each one of these spots right here. Okay, and again, I will stress that later on, but for what we know right now, we will have the population parameter for us. Okay, so this is what we call standard error, and we use these two pieces, bias and precision, to help us evaluate the method. Okay, we use these two ideas. So a little math. Okay, so you're definitely going to be using that graphing calculator to do some things. You got a little bit of subtraction and then a little bit of square rooting and stuff right here. It's very, very simple formulas. All right, so moving on. So I want you to think about bias and precision in this kind of idea. Okay, so this is a golf kind of metaphor. So you can see the cup, and you can see that each one of these represents like a shot towards the cup. In golf, they use what we call accuracy and precision. Think of accuracy like bias. Okay, accuracy means that we want to be exact or close to the population parameter. So think of the hole like the population parameter. Okay, so in this picture, this is good accuracy. You see how all of our balls right here, which represent like a p hat, a sample proportion, are really, really close to the hole. Okay, this right here is good accuracy because we're all really, really close to the hole. Okay, this is poor accuracy. This is poor accuracy because I have a lot of points, a lot of samples out here that are far away from the hole. Precision, okay? Precision is repeatability. Are all my shots close together or are they far apart? If my shots are close together, that's good precision. If my shots are far apart, okay, then that's bad precision. All right, So just kind of talking about some things that you see right here. This is good precision. So overall, as a statistician, this is what we strive for. High accuracy, high precision. Okay? This one, I think I said this was pretty good accuracy. I mean, like, it's okay. I would say the accuracy is, I mean, based off of, going through here, because we're trying to illustrate the different ideas. This one, the accuracy, it's a little bit lower, but it has good precision. Every time we hit, we're over here to the right of the cup. So this is good precision, poor accuracy, because we would like this to be over here. And when I mean poor, it's not that bad of accuracy because it's pretty close to the hole, as I said before. But this would be the idea of good precision, poor accuracy. Down here, looking at the other two, this is poor accuracy, poor precision. Okay? Poor accuracy, poor precision. All right? Because I've got balls everywhere. I've got it above, I've got them below, I've got to the right, I got to the left, and we're all scattered far away from the hole. Poor accuracy, poor precision. Over here, poor accuracy and kind of poor precision as well too. Okay? But the precision is actually a little bit better over here because we have our balls all over here on the right side. Okay? The precision's a little better. We're hitting it all in the same direction, but the accuracy's still off and the precision is still off. It's not as clumped together. Okay? So that's kind of an idea of precision and accuracy. Okay? And remember, accuracy is like bias. We want to be as close to this as possible. The further we are away from this, the more biased our results are. Okay? So this is pretty unbiased. This one is not too bad with the unbiased. These two are very biased. We're far away from the hole. Okay? These two have pretty good precision. Actually, the same thing kind of over here. It's not as bad as this, but at least everybody's over here on the right side. But up here, we're hitting it right to the same area. Okay, that's good precision. We're hitting it right to the same area. They're all clumped in here. Here, we're hitting it everywhere. Here, we're always veering off to the right. Okay? So there you go. That's kind of an idea, the way of think of bias and precision in a more tangible kind of form. Okay? All right. A little bit of extra information for us just about this. 1. Precision, so you know, does not depend on the population size. Okay? Precision does not depend upon population size, but precision depends on sample size. Okay? The larger the sample, the smaller the standard error. Okay? The larger we make our sample size, the smaller our standard error is going to be. Okay? The better the precision. All right? So that's important. Large sample size is good because that creates a smaller standard area for us. All right? Other things. The population proportion never changes. That's important. Your population proportion always stays the same. It is your sample proportion that changes because when you sample, different things happen on different samples. Okay? Remember, samples that were taken are like surveys. When you survey one day, you might have a high volume. When you survey the next day, you might not have that same high volume. You'll have a lot, but not as much as what you had the first day. So your sample proportion for that day will change. But the population proportion is always constant because it is out of everybody. And that doesn't change when it's out of everybody. The SE formula only works if the following conditions are met. So this is important. That standard error formula only works if we have the following conditions met. All right. 1, the sample is random, and it can be with or without replacement. It doesn't really matter. Okay. So as long as our sample is random, we like that. With or without replacement. Most of the time, guys, we're going to be doing without replacement, just so you know. But it's okay with. And then the second condition, because most of the time we're going to be doing without replacement, we need to make sure that the population size is huge. In other words, the population size must be bigger than 10 times the sample size. So whatever our sample size is, multiply it by 10, and as long as your population is bigger than that number or equal to it, you're okay. We can run the standard error formula. So 2 things. Sample is random. Population must be huge. And we only worry about this if we do without replacement. We only worry about a huge population size if we do without replacement. Okay? I don't think I have anything below that. Oh, yep. Also, when using the standard error formula, okay, it also means that your p hat is 0 or unbiased. So when we run this standard error formula, it means that p hat is 0 or unbiased. Okay? So kind of some important information, little extra pieces of information about precision that you need to know. Okay? All right. So let's take a look at what you're going to see. So right here, we've got a problem. It says a large collection of 1-digit random numbers should have 50% odd, 50% even. Okay? Because 5 of the 10 digits are odd, 5 are even. So right down below here, I want you to find the proportion of odd number digits in the following lines from a random number table. Count carefully. All right, proportion. Again, remember I talked about this in 7-1. It's like a fraction. Okay? I have a total of 1, 2, 3, 4, 5. Each group is 5. There are 6 of these, so there are 30 numbers total. I want to know how many of them are odd. Well, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Count that up again just to make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So if you go to your calculator and you take 17 divided by 30, we get 0.5666 repeating. So make sure that you also pay attention on these because this does want this as a decimal, so 0.56 repeating. So make sure that you round accordingly. Sometimes it says 2 decimals, sometimes it says 3, sometimes it says 4. Okay? And now I want you to answer the rest of the questions. And go. All right. So part B, it says, does the proportion in part A represent p hat or p the population proportion? In part A, because this is a sample, we are working with p hat. Okay? So this right here is your p hat. Okay? And then in part C, all they want you to do is find the difference. Okay? They want you to find the bias. That's what part C is all about. So all we're going to do is take our decimal, that p hat, and subtract it from p. Okay? Because up here, these guys right here are p. Okay? So when we come down here, and I'm going to make this blue. All you had to do was take p hat, which is 0.5. I'm going to round this to 4 decimal places. Minus 50% is 0.50. So you just go to your calculator. 0.5667 minus 0.50, and we get 0.0667. So that is equal to 0.067. And there you go. Okay. There's the biased. If they want this as a percent, then you would just move the decimal 2 places, but I don't think they want it as a percent. Let me double check that. But that's all they're really looking for. That's it. See, nothing crazy. It actually does. It wants it as a percent. And it actually wanted us to give these up here as the percentages as well, rounded to 2 decimal places. So rounding to 4, that was actually pretty correct. So up here, just kind of looking at what the book wanted, or what your assignment's going to want, you would say that this is 56.67%. Okay. And then down here, because there's your decimal, you would say that this is 6.67%. And there you go. Okay. So just make sure that you read those directions carefully. If it asks for a percent, then it should be an integer with some decimals, most likely. If it asks just for the proportion, if you read those fine prints, it will tell you to round to decimals. Okay. So really watch that in case. If you see the percentage sign, then make sure that, you definitely should have some integers there in front. If you don't see the percent sign, then it's all decimal. Okay. It should be 0 point something, 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 something. Okay. So just keep an eye on that. See, nothing crazy. You're just finding some information. All right. So that was p hat minus p. I didn't finish my thought down here. Okay. Or you would have gotten the same answer had you have taken 56.67 minus 50. That would have given you the same answer as what we had right there. You could have also done that too. All right. Go ahead, pause the video, give this one a shot. I'm curious to see what you think. And go. So, according to the Mars Company, packages of milk chocolate M&Ms contain 20% orange candy. Suppose we examine 100 random candies. Okay, what value should we expect our sample percentage of orange candies to be? Well, hopefully on this one you said 20%. Okay, this is the population proportion. So in our sample, we should expect nearly 20%. Just like over here, our sample our population proportion was 50%. This was close to 50%. Okay. So our population proportion, which is this guy, we expect the same thing of our p hat. All right. What's the standard error? Okay. So now we're going to actually run that formula. So hopefully you did that. And again, we can use this because it is random. Okay. It is random. And we know that our population size is definitely bigger than 100 times 10, because how many M&Ms are there in the world? Are there more than 1,000? Definitely. Okay, so that's why we can get away with running our formula. And all we're going to do is plug in the p, take 1 minus the p, and divide that by the n. So inside here, when you actually plug it into this formula, it's got to be the decimal. Okay, can't plug in the 20. So we're going to put in 0.2 times 1 minus 0.2. Divide that by n. Sorry, not n. Divide that by 100, because that's how many candies we have. This is your n. And we're going to let the calculator do the work for us. Okay? And they want you to round to 3 decimal places. Okay? So if we go to our calculator, second x squared, alpha y equals, to put in our fraction, 0.2, parenthesis, 1 minus 0.2, scroll down to the bottom, 100. There we go. And we get 0.04. So not a lot of rounding that we had to do. 0.04. So that's the answer to part B. And then last but not least, fill in the blanks. We expect, well, hopefully right here, you put 20% orange candies, because that's from part A. Give or take the standard error. So turn this into a percent, and that's 4%. So we expect 20% to be orange candies. Give or take 4% from this. So it could be that there is 24% maybe in the bag, or 16% orange candies in the bag, somewhere between there. That's what this kind of give or take means for us, which we will talk more about once we hit up 7.4. Okay. There we go. All right. So right here, this is the longest problem you will see in your assignment. And this is the last problem we'll do, because right on the next page, these are the questions for 7.2, numbers 20 through 29. But let's go ahead and finish this up. So it says a population of college students is taking an advanced math class. Okay. In the class are 3 juniors and 2 seniors. Using numbers 1, 2, and 3 to represent juniors, 4 and 5 to represent seniors, sample without replacement. Okay. Draw a sample of 2 people 4 times. Once in parts A, B, C, and D. So part A represents the first time we're going to draw a sample. Part B represents the second sample. C is the third and the fourth. Okay. And then we're going to fill in the table that's below. All right. So let me show you how part A runs, and let me show you how part of the, well, actually you can see how part of the table gets filled in. So let's talk about part A, and then I'm going to have you pause the video and you do B, C, D, and fill in the rest of the table. So in part A, it says use the first line reprinted here from the random table to select your sample of 2. So you know the selections are underlined. So we selected 2 and 4. They want you to report the percentage of seniors in the sample. Okay? In other words, count the number of 4s and 5s and divide by 2. So there's only 1 4. We're going to divide that by 2. So it says report the percentage. So a half is 0.5, which as a percent is 50%. Okay? Now, when I come down here to put this in my table, the population proportion of seniors, okay? So this is out of the population. Remember, there are 2 seniors out of how many people total? 1, 2, 3, 4, 5. So that's why you see 2 out of 5, which is 0.4. Now remember what I told you a couple minutes ago about the population proportion, because these should be real quick to fill in. The sample was what we did in part A. We found 1 out of 2, which is 0.5. And then the error would be 0.5 minus the 0.4, which is 0.1. See, there you go. 0.5 minus the 0.4. That's how you're going to fill in the table. So go ahead and actually, I could probably fit this all in. Yeah, there we go. Go ahead now from part B all the way through part E. Complete the rest of this information. Pause the video and go. Okay, so finishing this up. So in part B, you can see what was chosen here, 3 and 1. So how many 4s and 5s are there? There are none. So that's 0 divided by 2, which is 0. So down here, as we talked earlier, remember population proportion, I said it a couple minutes ago. Population proportion never changes, right there. So that means in this problem, in this entire column right here, it's always 2 out of 5, 2 out of 5, 2 out of 5, which is equal to 0.4, 0.4, 0.4. Right here, we had 0 out of 2, which is 0. So if we take 0 minus 0.4, we get negative 0.4. Okay? Now we just do C. Notice they're going to start taking away the underlines for us. So here was the first person chosen. Skip 3. Skip 7. The next person chosen was 5. So here are the two people. How many seniors do we have? 1 out of 2, which is 0.5 or 50%, because they actually do want the percentages up there. Up here, since that was 0, that would be 0%. All right, so part 3 right here would be the same thing as what we did in part 1. 1/2, which is equal to 0.5, which is 0.5 minus 0.4 equal to 0.1. Okay, and then down here, part D. So it looks like the first person we choose is 4, because none of these are possible. 9, 8, don't do 4, no 8, 0, 9. The next person we choose is 5. So that's 2 out of 2, which is equal to 1, or in other words, 100%. So down here, this is 2 out of 2 equal to 1. 1 minus 0.4 equals 0.6. And there you go. That's part E. So we did E as we did all the other pieces. We just filled in the table. And that, again, finishes up 7.2. A little bit about accuracy, which is bias, and precision, which is your standard error. Okay? And from there, that's it. That's 7.2. See you next time.